Welcome back, process safety leaders, for another process safety leadership talk by Safe Energy Ops. My name is Felipe Rendon. I'm here with my co-founder, Joella Ponte. And today we'll be walking through a refinery fire and explosion at a Pennsylvania refinery. Now, in this video, you're going to see hydrofluoric acid escaping through a piece of ruptured pipe, eventually forming a gas cloud, catching fire and explosions. And we're going to be talking about how, as a process safety leader, what you can look out for to make sure that the integrity of your equipment is adequately understood, is being adequately inspected. We're also going to talk about how you can assess the health of your safety equipment, your safety barriers, the right questions to ask to make sure that your layers of protection are up to snuff. Finally, we're also going to talk about how you can assess a hazardous process at your facility in terms of the adequacy of the safeguards and layers of protection around it. In hazardous processes, it's important to really understand not only what the regulations are, but whether your safety equipment really is up to par with the potential consequence of that process. So make sure you stay tuned to the end for an opportunity to learn about how you can strengthen process safety leadership at your facility and implement these lessons learned. Hope you enjoy it.
June 21st, 2019. The Philadelphia Energy Solutions, or PES refinery in Philadelphia, Pennsylvania. A dangerously corroded pipe elbow ruptured, releasing process fluid into the refinery's hydrofluoric acid, or HF alkylation unit. The process fluid then ignited, causing a fire and series of explosions. The fire and explosions caused the release of over 5,000 pounds of highly toxic HF, launched a 38,000-pound vessel fragment off-site, and resulted in an estimated property damage loss of $750 million.
Thankfully, despite the urban location of PES refinery, the local community was not seriously harmed, but it could have been worse. Our investigation found that a critical safeguard intended to protect the local community from a release of hydrofluoric acid did not function as designed. If a large amount of hydrofluoric acid had escaped from the refinery, the consequences could have been disastrous. This incident should be a wake-up call to industry and regulators to take every step possible to prevent a similar event from occurring.
The Philadelphia Energy Solutions refinery was the largest oil refining complex on the East Coast and could process up to 335,000 barrels of crude oil per day. Within its hydrofluoric acid alkylation unit, the refinery produced alkylate, a high-octane blending component of gasoline. That was done by using hydrofluoric acid as a catalyst. HF is a highly toxic chemical that is particularly hazardous if a release occurs because it vaporizes, becoming airborne. Breathing HF can cause lung damage, and skin contact with HF can cause severe burns and death. On the day of the incident, the HF alkylation unit was operating normally. Shortly before 4 a.m., a board operator in the refinery's main control room performed a routine change in the configuration of the process within the unit. The operator increased the flow of process fluid in an area of the unit by a total of 7 barrels per hour. Stable operation continued, with no abnormal pressure or temperature changes in the unit as a result of these actions. But nevertheless, at 4 a.m., a severely corroded pipe elbow within the unit ruptured. Flammable process fluid containing mostly propane, along with a small concentration of HF, escaped through the failed pipe elbow. The leaking process fluid formed a large ground-hugging vapor cloud, about 10 feet high, that engulfed a portion of the unit. Moments later, the vapor cloud ignited, causing a massive fire. Approximately 30 seconds later, the board operator took steps to prevent the release of additional HF. This was done by rapidly draining the unit's 339,000 pounds of hydrofluoric acid to a special vessel called the Rapid Acid De-Inventory, or RAD drum. The RAD drum was designed to safely hold HF in the event of an incident. At 4:15, due to the ongoing fire, an explosion erupted in the alkylation unit. 4 minutes later, a second explosion occurred. At 4:22, a process vessel in the unit containing flammable hydrocarbons violently ruptured, causing the third largest explosion. A giant 38,000-pound fragment of the vessel flew across the Schuylkill River and landed on the river's opposite bank. Two other fragments, one weighing about 23,000 pounds and the other about 15,500 pounds, landed inside the refinery. The fire knocked out the control system communication to the refinery's HF water mitigation system, and the backup power supply to the system also failed. As a result, the refinery's elevated HF mitigation water cannons, which were designed to spray high volumes of water to help contain an HF release, could not be turned on remotely from the control room. The water mitigation system was a critical safeguard at the refinery designed to prevent released HF from going off-site. About 40 minutes after the release began, a refinery shift supervisor wearing bunker gear entered the unit and manually turned on a pump that allowed the HF mitigation water cannons to operate. Other refinery workers closed valves to stop the flow of hydrocarbons and steam into the unit. The fire burned for over 24 hours until it was finally extinguished the following day at about 8:30 a.m. 5 workers sustained minor injuries during the incident and response. The CSB is unaware of anyone off-site experiencing health impacts from the hydrofluoric acid release. The CSB launched an investigation into the fire and explosions and found 5 key safety issues contributed to the severity of the incident. They are mechanical integrity, verifying safety of equipment after changes to good practice guidance, remotely operated emergency isolation valves, safeguard reliability in HF alkylation units, and inherently safer design. The first safety issue is mechanical integrity. The CSB determined that the pipe elbow that failed had corroded faster than other piping in the HF alkylation unit. That is because the steel pipe elbow contained a higher content of nickel and copper than other piping in the unit. Carbon steel is commonly used in HF alkylation units, but is known to be susceptible to hydrofluoric acid corrosion. In refinery processes using some amount of HF, hydrogen fluoride reacts with iron in steel piping to produce iron fluoride. The iron fluoride then forms a film that coats the inside surface of the piping and protects the steel from corrosion. However, if the steel contains high concentrations of copper, nickel, or chromium, known as residual elements, the rate of corrosion is often higher. This is because the iron fluoride film that forms on steel containing high amounts of residual elements is less protective. The pipe elbow that ruptured in the PES refinery was installed around 1973. It had originally been constructed of a particular steel alloy that intentionally contained a higher concentration of nickel and copper. But by current industry practices, the high concentrations of nickel and copper in the pipe elbow meant it was not fit for service in a process using hydrofluoric acid. Yet the pipe elbow remained in service for over 40 years, corroding at a much faster rate than adjacent piping components that did not have high concentrations of residual elements. The CSB also found that PES and the previous owner of the refinery never inspected all carbon steel piping circuit components susceptible to HF corrosion. Such a program was not required in the standards set by the American Petroleum Institute, or API, for the safe operation of hydrofluoric acid alkylation units. But had PES or the former owner inspected all of the carbon steel piping circuit components susceptible to HF corrosion in the unit, they may have identified that the pipe elbow was corroding at a faster rate than adjacent piping components, which could have prevented the incident. After the incident, API revised its standard to include a new requirement for companies to develop a special emphasis inspection program to identify areas of accelerated corrosion in their refineries.
The new API Special Emphasis Program requires companies to inspect all individual carbon steel piping components in HF corrosion zones. This will prompt refineries to find any components that are corroding at a faster rate. This is an important safety requirement developed by API, and it should help prevent future catastrophic failures from this known safety hazard.
The second safety issue identified by the CSB involves verifying the safety of equipment after changes to good practice guidance. When the pipe elbow was initially installed in 1973, the standard set by ASTM International for carbon steel piping did not specify limits on nickel or copper content. Over the next decades, that standard changed, and by 1995, the ASTM standard had been revised enough that the pipe elbow no longer met its requirements due to the elbow's high levels of nickel and copper. Yet neither PES nor the previous refinery owner performed a comprehensive evaluation of all installed HF alkylation unit piping components manufactured to older versions of ASTM standards to ensure that the piping components were still safe to use.
To prevent catastrophic incidents, companies and industry trade groups must take swift action to ensure process safety when new knowledge on hazards is published. These actions must include ensuring that facilities built before the new knowledge was published are still safe to operate. Ensuring safety can include 100% inspection of all equipment and piping, equipment replacement, and other changes needed to prevent loss of containment events.
A third safety issue discovered by the CSB concerns remotely operated emergency isolation valves. The largest of the three explosions at PES occurred when a vessel located above the failed pipe elbow violently ruptured. The CSB concluded that a jet flame shot from the ruptured pipe elbow and heated the bottom of the steel vessel, which contained a large amount of flammable hydrocarbons. For over 20 minutes, the jet flame erupted from the failed pipe elbow, weakening the steel bottom of the vessel and causing it to stretch and thin. The vessel then ruptured, launching 3 huge fragments into the air. The CSB found that there were no emergency isolation valves installed in the HF alkylation unit to remotely isolate nearby hydrocarbon sources that could then flow through the failed elbow. And these valves are not explicitly required by the current API standard on safe operation of hydrofluoric acid alkylation units.
Prolonged releases and fires in HF alkylation units can cause equipment ruptures, compromise safeguards, or lead to releases of toxic hydrofluoric acid. Companies need to install remotely operated emergency isolation valves to quickly stop releases before they become catastrophic events.
As a result, the CSB made a recommendation to API to update its standard on safe operation of hydrofluoric acid alkylation units to require installation of remotely operated emergency isolation valves on the inlets and outlets of all hydrofluoric acid containing vessels and any hydrocarbon containing vessels meeting defined threshold quantities. The CSB found a fourth safety issue that contributed to the incident at the PES refinery, which is safeguard reliability in HF alkylation units. At PES, the HF alkylation unit was equipped with a water spray mitigation system that was a critical safeguard in the event of an HF release. The water mitigation system was designed to use cannons to spray large volumes of water at any HF release in order to suppress the amount of vaporized HF so that it could not travel off-site to neighboring communities. But when the control room operator tried to remotely turn on the water pumps that fed the water cannons, it was not possible because the control system communication to the water pumps as well as a backup power system in the unit had both failed during the initial fire. Although API recommends fireproofing these elements, it does not specifically require companies to do so. Instead, 40 minutes elapsed from the time of the release before a worker was able to manually turn on the pump. In the meantime, highly toxic HF was able to freely escape from equipment and vaporize into the air.
Hydrofluoric acid alkylation units present unique hazards due to the presence of highly toxic HF alongside large quantities of flammable materials within one unit. The damage to the water spray mitigation system at PES demonstrates that active safeguards, or safeguards that require a person or technology to trigger their activation, have the potential to fail in major incidents involving fires and explosions. Critical safeguards and their associated control system components must be protected from fire and explosion hazards.
As a result, the CSB made an additional recommendation to API to update its standard to require protection of critical safeguards and associated control system components from fire and explosion hazards, including radiant heat and flying projectiles. And to help ensure that new API safety requirements and recommendations are implemented effectively nationwide, the CSB recommended that the EPA should develop a program that emphasizes inspecting refinery HF alkylation units to verify that companies are complying with API's standard. The fifth and final safety issue highlighted by the CSB in its report on the incident at PES is inherently safer design. Of the 155 U.S. petroleum refineries currently in operation in the United States, 46 operate HF alkylation units. But hydrofluoric acid is highly toxic and is one of the 8 most hazardous chemicals regulated by EPA's RMP program. The other acid catalyst used in refinery alkylation units is sulfuric acid. Although sulfuric acid is highly corrosive and can cause skin burns upon contact, it remains a liquid upon release. Therefore, it does not present the same risk to surrounding communities as HF, which vaporizes upon release and has the potential to travel off-site. In addition, alternative alkylation technologies have been developed. These include a solid acid catalyst, as well as the new ionic liquid acid catalyst, which was developed by Chevron. Using a sulfuric acid catalyst or other new alkylation technologies would prevent off-site human exposure to HF in the event of future incidents. Replacing highly toxic chemicals with less hazardous chemicals is an inherently safer design approach.
Currently, there is no federal regulatory requirement for refineries to analyze inherently safer design strategies to reduce the risk of serious accidental releases. Technologies are being developed that could be safer alternatives to HF alkylation, and refiners should periodically evaluate these available technologies.
In its report, the CSB recommended that the EPA require petroleum refineries to conduct a safer technology and alternatives analysis as part of their process hazard analysis, as well as evaluate the practicability of any inherently safer technology, and initiate prioritization to evaluate whether HF is a high-priority substance for risk evaluation. If it is, conduct a risk evaluation of HF and implement any identified corrective actions as required by the Toxic Substances Control Act.
The destructive event at the Philadelphia Energy Solutions refinery exposed weaknesses not only in PES policies, but also industry standards and federal regulations. We call on the American Petroleum Institute, the refining industry, and the United States Environmental Protection Agency to implement our recommendations and help make sure that another catastrophic incident in a hydrofluoric acid alkylation unit never occurs. Thank you for watching this CSB safety video.
All right, so that was a lot of information, right?
Yep.
Okay, so after watching this Philadelphia incident, obviously these are the 5 key safety issues that were the areas of recommendation from the Chemical Safety Board. Why don't we go ahead and start with mechanical integrity, obviously coming back to the rupture piping and the lack of inspection program around, carbon steel piping and service of hydrofluoric acid. I hope I said that right. What comes to mind as a process safety leader, Felipe, in a site? It was mentioned here that I guess this site has been, has exchanged ownership, right? So
Right.
You don't know what you don't know type of situation. Comes to mind as a process safety leader in your site in terms of mechanical integrity as it relates to this event.
Yeah, as a process safety leader, it can be tough, to be honest. Just be able to in your day-to-day job understand or be aware of the integrity of your equipment, to be honest. Some things might be glaring at you, some obvious, leaks and seeps and leaks, for example, obvious issues. Piping, material wall thickness is pretty hard to tell just by looking at it, right?
Yeah.
So what can you do as a process safety leader? As a process safety leader, you really have the authority to ask the question, first of all, what does our inspection program include? What does it look like? And if it doesn't seem to be including everything that you think it should, you should speak up. You should speak up and escalate. So when you do your safety walkdowns, which hopefully you're doing on a regular basis, and you do see piping or equipment that seems suspicious because it has a lot of rust on the outside, it's exposed to the elements versus other piping that might be covered with insulation, for example, or even insulated piping that you don't think has been inspected in a long time, because of course, corrosion can happen under insulation. You have the right to ask the question, first of all, what does our inspection program look like? Does it include this piping? In this particular example, they did have inspection programs in place, it seems like, but they didn't cover this section of piping. Correct me if I'm wrong. What I gathered from the CSB video was that API actually didn't require for HF alkylation units necessarily inspection of the piping, the area where this piping was located, I believe. Now, again, makes it tough. And you and I have been in this situation, right? Where the regulation might not say it. Maybe your superiors aren't really talking about it or don't seem concerned about it. So it feels like you don't have a leg to stand on if you were to raise a concern, right? But that's why process safety leadership is such a critical piece of operations, is a critical factor, because as a leader, you've got to state your case and you've got to build a culture with your peers as process safety leaders that takes concerns seriously like this and investigates further. So, in this particular case, I'm not going to say that it would have been easy to have seen this coming, but we don't know everything of the process safety leadership culture in this particular facility. That's what inspection programs are for. And as a process safety leader, you should raise some flags if you notice that in this example, this pipe was in service for 40 years and it looks like it was never inspected. So you should be able to raise a concern and say, hey, look, there's piping here that we haven't inspected since this place was installed and constructed. We should, I would like for us to inspect this piping, because if there's a thin wall somewhere, given how deadly the fluid is inside of these pipes, I want to know where we stand. As a process safety leader, you have that right. And it also goes back to knowing the properties of your process, of your system, knowing what your hazards are. Hydrofluoric acid, the CSB stated over and over, is a very toxic, very hazardous chemical. And so you should have that in mind. Again, in your state of unease, your chronic unease that we promote and Safe Energy Ops, have that in mind, have that push you to ask the right questions. That's my thoughts on that.
Yeah, absolutely. I'm not sure if you kind of heard the same thing I did, but it seems that piping that was installed, due to the amount or the mixture of metals, and I'm not, an expert on metals and, and materials for piping, but it seems that was, one of the findings was that it was not quote unquote fit for service, right? The amount of, I don't know if it's a carbon steel or the nickel, was just, not right for the service. And so definitely not something that you're going to see, just like you stated, just, being on the day-to-day doing your walks. But, I think this highlights the necessity to share lessons learned, to share findings, right? Just like we're doing with this content, we're having process safety leadership talks. That doesn't mean that you have to be a chemical engineer. You could be a mechanical engineer that's focused on rotating equipment, or somebody that's focused in another area. But are you looking and sharing knowledge that's coming up, right, to see if it's applicable to your site? And so as things progress and information is easier to gather, if in fact the piping components were not fit for service. Maybe at the time that it was placed, it wasn't known. Maybe it's it's kind of an afterthought. But just think about always keeping up to date with these new findings. Obviously, this incident highlights what sounded to be over 50% of refineries in the US in terms of their service and what they're going to do about it. Just getting into the habit with your teams on sharing current lessons learned may help prevent any future process safety events.
Right. If I could say something on that, Joel.
Yeah.
In Safe Energy Ops, we promote having process safety embedded in the culture through process safety moments, presentations about industry incidents and local incidents. So after an incident like this, talking about all the other refineries that are in similar situations that perhaps have piping that fall in the same category, might have met the ASTM standard when the refinery was built, but since the ASTM standard changed, hasn't been evaluated to see if it's in need of equipment change. Those other refineries, do they have a culture of sharing these incidents, making sure that they're up to date, presenting this, because it's very, very helpful in terms of the process safety at their facilities to learn these lessons, as you said, from incidents that have happened. So, in this particular case, they might not have had a warning or a red flag happen before this incident, unfortunately, and thankfully nobody was seriously injured. But other refineries, it's just as important that they take this into account and perform those evaluations. That's where leadership comes in finding these things and presenting, building that culture to say we're going to be eyes and ears perked to learn from our industry and from other facilities around us.
For sure. So on this second bullet item, verifying safety of equipment after changes.
Yeah, I would say that
practice guidance.
That would be the ASTM standard for the piping. ASTM standard changed, but neither the previous owner nor the new owner of this Pennsylvania refinery did the evaluation to see they needed to make changes because some of their piping fit the old ASTM standard and not the new one. And I'm going to be honest and I'm going to be blunt. It's not easy oftentimes to pinpoint these changes and perform these evaluations when you've got just a lot of
going on,
a lot of things on your to-do list. That's why support systems and collaboration channels are so important. Step 3 of our align phase, get those collaboration channels in order so you can get the right information to you and shared between different parts of the company.
Yeah, for sure. I mean, it seems like right now, just going through these 2 bullet items, to me, there's 2 keywords. One is share. Right? Share, go ahead and share the message, share any lessons learned. And then 2, like you said, communication channels, like a good question to ask ourselves for our sites and everybody's sites out there, whether you have HF or not in your facility, is do I have a process in which we receive updates to verify applicability for my process, right? Whether it's from regulators, policies, good practice journals. Because, as you said, we're focused typically on the operations side. We're focused on keeping the plant safe, reliable, operating the personnel. But it doesn't hurt to just ask ourselves, not saying it's simple, not saying it's easy, but it doesn't hurt to ask ourselves, do I have a channel of collaboration, a direct path of this news comes, I'm getting the info that I need so I can actually see if it's applicable to my site from these good practices. So not easy, but something definitely to take away from this incident.
And I'll add this, Joel, to an operation, a facility, a plant always has a lot on its plate. That's the norm. But as process safety leaders, we've got to create the space for process safety, for looking at incidents, lessons learned, for taking them seriously. Managing your workload, it really comes down to that. And so if you don't have a structured way of looking at these lessons learned, whether it be on a regular frequency, whether that's once a week or once a month, then chances are you won't notice these things. So you've got to manage your workload, right?
Absolutely. Thanks for sharing that, Felipe. So 3rd bullet item here is remotely operated emergency isolation valves. And as we went through the incident, I'm sure the same thought went through your mind is like, where are the automated shutdown valves to stop the bleeding, the feeding of this fire and what's going on here. I think this is especially a red flag for sites that are really old or small operations that maybe are not doing as thorough of a PSM program. Kind of, asking themselves, hey, if this chemical's bad, right? If this chemical's bad, do I have a way to shut down automatically the flow to it?
Yeah, I believe that the video said that API standard actually didn't require it for HF units, and they recommended that the API update their standard. And I can't remember if they said that API did.
And this event, kind of along those lines, I think it's very clear that it is a shared responsibility, maybe not accountability, but it's a shared responsibility between regulators and operators, right? If you see that a chemical process does have hazards, and just before walking into the call, I remember now listening to an interview of a gentleman that used to work around HF in this facility. Actually, he stated the message that HF is dangerous is something that is remembered, talked about pretty frequent, and the hazards and the hazards opposed to like maybe H2S, like they said H2S doesn't really vaporize once it's outside of the pipe, but this one does. And so what I'm trying to say here is, even though the regulator or the general good practice may not require it, and I think this kind of ties into inherently safer design at the same time, it's okay to question. It's okay to raise your hand and say, don't dismiss a safeguard just because the standard doesn't require it. Right. Hindsight 2020, sure, kind of easy to say after the event, but I'm just trying to encourage folks to, whenever they're having these design conversations and HAZOP, LOPA conversations and process safety leadership conversations, if you see a dangerous process in your facility, at least this is my takeaway. If I see a dangerous process in my facility, would I be able to shut it down remotely?
Yeah, that's right, Joel. And I mean, for me, it comes back to asking the right questions as a process safety leader. Process safety takes everybody. And in this case, engineering would be the department to really put the solution in place with the remote operated emergency isolation valves to make sure that they're fit for the hazard. And you and I have both been through many HAZOP LOPAs, and in your hazard operability and layers of protection analysis studies, you rank the hazard. And in this case, it would be a release of hydrofluoric acid. You model it and you see what the consequence looks like, and then you determine whether your layers of protection are sufficient. In that room, you should have engineering, automation, controls, but you definitely need to have someone from the operations team as well to say, the regulation doesn't require it, but I feel that the consequence is high enough here, and the probability as well, that we should go ahead and put in a remotely operated emergency isolation valve that works on an independent control system, for example.
Because it's that's a very good point. That's a very good point. I could see the conversation or the question being raised definitely in a HAZOP LOPA scenario. Interesting that maybe if there was a recommendation, maybe there was a recommendation and it wasn't implemented. There's definitely a shared response, a shared set of lessons learned here, not only for operators, refineries, but also the regulators as well in this event.
And that reminds me of another point. Where you and I come from, we definitely put in layers of protection that weren't required by regulations. We let HAZOP LOPA drive us sometimes to higher levels of control, and I respected that, and I was thankful for that. But what I also noticed was that recommendations that might come out of HAZOP LOPA sometimes took way too long to implement, and in that time, in that time you are at risk. I'm talking about existing facilities. Whenever you do your HAZOP LOPA revalidations. And so point I want to raise is back to workload, as I mentioned before. Feeling is still fresh in my mind of having the recommendations from your HAZOP LOPA just stacked onto the pile of things that already needs to be done for the facility, and how do you prioritize that? And that often is a $1 million question. The thing is, your ability as an organization to implement needs to be on par with your process safety risk needs. So what I mean by that is in a case where a recommendation comes out to install emergency isolation valves, for example, if it takes you 4 years to implement, you should really take a look at whether your process for implementation could be streamlined, and you could really streamline your defect elimination. That has to be balanced, of course, with all of the right engineering checks and balances to make sure that you're doing everything correctly in terms of specifying equipment to the right standards, and even the procurement side, of course. You know, every facility, every company has their process, but you've really got to look at if it can be streamlined in such a way that you're not feeling like you're always adding more and more onto an ever-growing list, because that's a recipe for and very important things to slip through the cracks and just fall into never land and never get done.
Absolutely. All right. And then I guess the safeguard reliability in HF alkylation units, and I'm assuming this is talking about the
water
was it
cannons.
the water cannons and the instrumentation and the power to them being affected by the initial explosion and I guess fire. And so this is more of a mitigation, right side of the bow tie. You know, the event's already happened situation. If we're going to take credit for stuff like that, you know, you got to make sure that it's being checked up on and it's protected. Obviously they updated the requirements here after the incident. From a practitioner standpoint, what's going through your mind as you see this incident and seeing that it keeps escalating because the mitigation tools that we were thinking were available are not working?
Yeah, you know, you've really got to look at the engineering and design. Did you have an independent power supply to the pumps that supply those water cannons? I understood the power to the pumps failed as a result of the fire. May not have been preventable. The things that you look at when you design your power supply: redundancy, independence, so that there's no single point of failure, right? Your power supply to the pumps is on your emergency support system, not your control system power, for example. Now, the things that I'm mentioning are engineering factors, right? Which, as we've said before, process safety should be embedded everywhere. As a process safety leader, which is what we focus on, I think it comes back to knowing the design and the status of your layers of protection and asking the right questions. As a process safety leader, you should be aware of how the cannons work, and it does seem like that they were at this refinery, being that one of the supervisors actually went out and established power to the pumps. When you're taking the time to understand your layers of protection and you notice that there might be a single point of failure, you have to have the courage to ask the question, is this sufficient mitigation for us? If we were to have a fire, it seems to me like we could lose lose power to the very devices that are intended to mitigate against that fire in the first place. So not easy things to be aware of, and not easy things to escalate. But as a leader, you want to have an eye for those things, and you want to create the culture to where if someone else notices it, they can escalate it and it be taken seriously.
Two questions come to my mind as a takeaway from this line item. You know, if I'm on deck, if I'm on site, and that is if I see a mitigation tool, a mitigation equipment, is how often is it inspected and how is it protected? If you ask those two questions, you're going somewhere, right? Because if you find out it's not tested enough, then how can you really rely on it? And then if you figure out that it's not protected from an explosion situation that arises, like you're saying, it's not plugged into the emergency response system, or it could be affected physically by something going on, then can you really rely on that mitigation measure? Personally, I've always struggled with mitigation layers being called safeguards, you know, because to me, you're just preventing escalation at that point. That would be kind of the two questions, you know, if I were on site that I would take away. And as I'm doing my walkthroughs, I would be thinking, to simplify this, I would be thinking, okay, how often is this inspected and how is this protected? If that makes sense. So yeah, anybody can do that as a process safety leader. Would you agree?
I would agree. And they did mention actually that the CSB made a recommendation. I forget which entity it was that governs this, but
EPA, I
to-
think it was EPA.
Yeah, I think you're right. I think it was the EPA to make them require mitigation systems to be fire protected in an area that's susceptible to fire risk. And so to your point, those are the questions that as process safety leaders we should be asking, independent of the regulations. It's good that hopefully the regulation is updated to learn from this, but having that process safety knowledge is going to cause you to ask those questions. Maybe take some steps, even if the regulations don't.
Makes sense. And then last but not least, inherently safer design. When you hear that concept, I know we've worked through this concept quite a few times, but it can feel, I can say from the deck standpoint, from the day-to-day operations, unless you're dealing with some sort of big equipment package delivery, sometimes it could feel out of context because typically stuff arrives on deck, already designed. And like in this instance, you had a vessel on top of a vessel with an elbow that wasn't inspected, that I guess they didn't really know that wasn't fit for service until hindsight 2020. In terms of inherently safer design for the day-to-day process safety leaders, what comes to mind as you see this, or maybe in conversations that could relate to this?
Well, I think what the CSB was getting after was, instead of hydrofluoric acid, you could use sulfuric acid in your process, or you could use the ionic catalyst they
New
mentioned.
technology, I guess it's like newer technology developed by Chevron is what I think they said.
That's right. And those technologies, those other materials don't have the same risks as hydrofluoric acid. Would it require a huge investment to change to the new material, new technology? I'm definitely sure it would. How serious are you about process safety? So
does having an incident. So does
Yeah.
having an incident, right? I mean, that's
how long term are you looking? Yeah, exactly. How long term are you looking? And what I think a lot of companies miss is that long term outlook. A lot of companies make the mistake of looking too short term and just looking for something that'll get them to the next year or to the next quarter. It's hard to quantify what you save yourself in costs by making a big change like you would be making by changing the catalyst or in this process. It's hard to quantify because, as I mentioned in the last video, you could make this change to an inherently safer material and spend a lot of money. 5 years down the road, everything's going well. 10 years down the road, maybe you finally have paid off the investment and you're making money. If you compare that just on a cost basis or a financial basis to not making the change and perhaps making other small tweaks, of course, the financial analysis is going to say, stick with what you have and try to make tweaks elsewhere, and et cetera. The thing is, nobody has a crystal ball to predict an incident like this. It's about the process safety culture and how seriously you take process safety. As a leader, you've got to have a long-term mindset without sounding too cheesy. Sometimes you've got to have a bit of faith that the choices that you make in improving process safety will pay off, that they're going to pay off over the longer term. Not only that, but everybody's going to be safer, which should be the most important thing.
Absolutely. So just, have that, again, it's about having that chronicle uneasiness around process safety leadership and figuring out, okay, is there a better way? What's out there? Is there new technology? How can I get my hands on new lessons learned and see if it applies? I mean, sometimes it may not apply, but the 1 or 2 times that you get a shared lesson learned, a new technology that could apply to your site, you're talking about saving lives, saving reputation, saving equipment, millions of dollars, right? All right. Well, I think that covers it in terms of the kind of the 5 key takeaways. Any other key points that you want to discuss today regarding this incident, Felipe?
Well, I do want to make a point about the operator response. It seemed like the control room operator acted in a way that helped de-escalate as much as was possible by sending hydrofluoric acid to the reservoir that's intended for, emergency de-inventorying. And so I wanted to highlight that because to me is showcasing the knowledge of the process, but also process safety knowledge of that operator. And so as process safety leaders, we want to make sure that our operators are up to date and understanding of their hazards, their layers of protection, if this happens, what do I do? If this happens, what do I do? Very, very important, very key. And I just wanted to stress that.
Absolutely, absolutely. Well, folks, thanks for joining us in this process safety leadership talk. In the case that you have not yet joined our free increased process safety leadership challenge, where we take you step by step, where you can actually go ahead and complete a self-assessment for your site or your process safety leadership in a sustainable manner. It's completely free. You can go to safeenergyops.com, join the community, join the conversation. We are passionate about increasing sustainably process safety leadership so that we can all return back home together. So feel free to join the challenge. Everything is 100% online. Great networking opportunity, great opportunity to walk in and get some perspective and share some lessons learned and download some good resources. So what I'm sharing right now on the screen is kind of our 3 phases and our 9 steps you can get absolutely for free by joining the Increased Process Safety Leadership Challenge. So if you are yet to go and sign up, again, go in there, 100% free, spam free as well. We're just looking to help sites and process safety leaders with some tools to help increase the process safety leadership on your site. So if you enjoyed this video, make sure you like, subscribe, share with a friend, share with a colleague. We're just doing these videos so that we can help you and your site continue the process safety leadership talk and conversations. All right. Until next time, see you guys on the next video. Take care.